Oh, I'm recording. Okay. Hello, everyone. Welcome to another video. I'm back with some calculus for today. So today's one is going to be fun. Please like and subscribe once again. Share it with people who might find this useful, but everyone will find this useful. So share this video with everyone, pretty much. Today I'm just going to use light mode. The integral for today is, let's call it I equals 1 over a plus b cosine of x dx. So it's just a general form type of a integram where a and b are constants and x is the variable. I'm going to use something called the Weierstrass substitution, which is it looks awkward at first, but I'll explain it well to you, hopefully. So the idea is we take a substitution t, our new variable, equals tangent of x over 2. How's this going to work out? How did we get tangent from cosine? I don't get it, you may say. Well, the guy who came up with this, I think he did a lot of brute force and he came up with this. Well, you're going to see how it works. So what we need is something like cosine of x in the form of a function of t. We need sine of x also in the form of a function of t, and we need dx in the form of a function of t dt. I think it's wrong for me to use f every single time. I'll use g and then h. Let's do it. Okay. G, h. Alright, cool. How do we derive these? How do we get them? Before we get them, let's construct a right angle triangle using this. So this tells us that if we have a right angle triangle, this doesn't look like a right angle triangle. This looks like a wedge, but I'll still use it. That's the right angle. This is the angle x over 2. The definition of tangent of an angle basically means the angle is the value you get when dividing the side opposite here by the adjacent side here. And then this is just the hypotenuse. H, O, and A. I'll label them like that. So in our situation, t can be written as t over 1. It's t over 1. So that means that the opposite side is t and the adjacent side is 1. So that tangent of x over 2 is equal to t. We need to do something else. We need to work out what h is. Well, h, if we use Pythagoras' theorem, is equal to t squared plus 1 squared, all with a square around it. So 1 plus t squared. By the way, I should emphasize this to you. Here, this a that I was using is not the same as that a. It's a different a. I'll just write capital A then, just to make it simple. Right. A, O, and H. There. Okay. So sine of x over 2 is equal to the opposite over the hypotenuse, which is t over root 1 plus t squared. And cosine of x over 2 is equal to the adjacent over the hypotenuse, which is 1 over root 1 plus t squared. Now we have x over 2 with the sine and x over 2 with a cosine. What we need is just x, not x over 2. So to do this, we need to utilize something called the double angle formula, which goes like this. Sine of an angle, let's just call it, I don't know, alpha, or let's call it 2 alpha, sorry, is equal to 2 sine of alpha cosine of alpha. So this basically means that sine of x is equal to 2 sine of x over 2 times cosine of x over 2. If it helps, I'll just put brackets around the input like that. That bracket looks like a heart. I don't like that. Okay, that's better. Yes. I don't think my microphone is good quality, but I'll try my best. So from earlier, sine of x over 2 is equal to t over root 1 plus t squared. And cosine of x over 2 is equal to 1 over root 1 plus t squared, which, if you simplify, is equal to 2t over 1 plus t squared. The reason we removed the square root is because this bit here, we're squaring it basically. We're multiplying it by itself. The square root gets cancelled. So this is equal to sine of x. Of course, we don't need this for that for this particular integral, but it's nice to have. We may need it for another integral, maybe in another video, who knows. That's a notif. So another addition formula that you'd need to know for A levels, for probably Calc 2, is this. Cosine of 2 alpha is equal to cosine squared of alpha minus sine squared of alpha. And there are many forms of this identity because of the fact that cosine squared of alpha plus sine squared of alpha equals to 1. You can replace this cosine squared of alpha with 1 minus sine squared of alpha, and you could replace this sine squared of alpha with 1 minus cosine squared of alpha. But for the purposes of this particular situation, this form of that identity is more beneficial for us. So if I write this in terms of x, cosine of x is equal to cosine squared of x over 2 minus sine squared of x over 2, which is equal to, what is cosine of x over 2? It's this. So 1 over root 1 plus t squared. And we square all of this. And we do the same thing with the sine. So t over root 1 plus t squared, all squared. And now, from your knowledge of fractions, you can basically say that squaring a fraction like this means that you square the numerator and you square the denominator. 1 squared is just 1, and the bottom squared, you just cancel out the square root. So I can rewrite this like that. There we go. I can do the same thing for the other fraction, and you get this. Let me just take the square root off. There. And then I put the fraction line. Alright, so that's what cosine of x is. Now, what do I have? I have a sine of x in terms of t. I have cosine of x in terms of t. Finally, what do I need? We need, because you're watching this with me, we need dx in terms of t. So, from earlier, if tangent of x over 2 is equal to t, and we apply arctangent to both sides, we get x over 2 equals arctangent of t. Now, let me know in the comment section, do you prefer this notation or do you prefer this notation? And if you say you prefer this, it doesn't mean I'm going to change the way I notate things just to suit you. It's just, just for interest. Then I can bring this 2 to the left, to the right hand side, sorry. I forgot my right and left there for a second. And x equals 2 arctan of t. Now, if we implicitly differentiate both sides, dx is equal to 2. Okay. For those of you who don't know how to differentiate arctan, you end up with the square root of 1 plus t squared. Now, if you didn't know this, let's suppose we didn't know this because, this is probably year 2 A-level stuff. For those of you in America, you wouldn't know what that is. Don't worry about it. If we didn't know how to differentiate arctan, then we would have to differentiate straight from here. So the tangent of x over 2, if you differentiate that implicitly, you get secant squared of x over 2 multiplied by the derivative of the input. The derivative of the input is just a half, so I put half there. And put dx, and we differentiate t, we get dt. And then we can bring the secant squared to the other side, right? I think. Am I making a mistake? Oh well, but let's just rub this out and do the thing that I was doing earlier. So x equals 2 arctan of t, and dx is equal to 2 over root 1 plus t squared dt. How do we know this? Well, let me just show you another case. Let's say you have something like d over d. Give me a variable, somebody give me a letter. D over d w arctan of w equals, how do you find that? How do you differentiate arctan of w? Well, to do that, we can let arctan of w equal a variable. Let arctan of w equal y, for example. Apply tangent to both sides so that w is equal to tangent of y. implicitly differentiate both sides so that dw equals secant squared y dy, and then what you do is you need dy over dw. So d over dw arctan of w equals to dy over dw, which equals to 1 over secant squared y. Basically, what I did was I brought this there to the right hand side pretty much, and I brought that to the left hand side, and I switched the left and the right with each other. So you end up with 1 over secant squared of y, which is cosine squared of y. And if I draw you a triangle where tangent of y is w, and I work out the hypotenuse, which is 1 plus w squared all the square root. This is the same as a triangle we did in terms of x and t earlier. If you want to refer back to that, why not? Well, cosine of y is equal to the adjacent over the hypotenuse. If you square both sides, then you have to square the right hand side as well, and you end up with 1 over 1 plus w squared. So therefore, if you differentiate arctangent of a function, you get 1 over 1 plus that function squared. Let me rub all of this out now. We don't need it now. I've shown, like, to those of you who are in like probably your first year of A levels and you didn't know how to differentiate arctangent. Well, now you do. So back to this. So the reason I have a 2 here. Wait a minute, I don't need this square root. That's a mistake by me. Sorry. The reason I have this 2 there is because I had a 2 on the outside. So the 2 there went there. It's a constant multiple, remember? Now, if I rewrite the integral in terms of t, what do I get? I is equal to, from earlier, I'll just copy it down, a plus b cosine of x dx, which is equal to the integral of 1 over a plus b. What is cosine of x? From earlier, cosine of x is this, which we can rewrite by combining the two fractions together since they have the same denominator as 1 minus t squared all over 1 plus t squared. 1 minus... So I'll write all of this there. If my pluses and my t's look similar, then I apologize. And dx can be rewritten as 2 over 1 plus t squared dt. And this 2, we can bring it to the outside because it's a constant multiple. And we have 1 over the bottom. So what we need to do is multiply this bit by that bit. And to do that, you need to multiply the a by the 1 plus t squared. First, you end up with a plus a t squared. And then next, you need to multiply this bit with the b by the 1 plus t squared. What ends up happening is the 1 plus t squared cancels with the 1 plus t squared there. And you end up with b times 1 minus t squared, which is plus b minus b t squared. We still have dt from earlier. If I write this integral nicely now, you can rewrite it as a minus b times t squared, and then plus a plus b dt. So now let's take a little substitution. Not a calculus substitution per se. I'm just doing this to make the constants look nicer. Let's say a minus b is equal to c1, and a plus b is equal to c2. Let's say instead of c2, let's say okay, c2 is fine probably. So now if I rewrite this integral in terms of dt and the c's, you end up with 1 over c1 t squared plus c2 squared. So not, okay, I don't need the squared, my bad. And then we have dt. How do we integrate this? Well, those of you who know it, you will know. I'll put it that way. But those of you who don't know, I'll show you. Let's write this for now. So what I'm going to do is divide the denominator, the entire denominator, by c1. So I end up with t squared plus c2 over c1, right? c2 over c1, like that. If you divide the denominator by a certain quantity, it's the same as multiplying the numerator by that same quantity. So it's like if I multiplied 1 on the top by c1, but except I'm playing with the denominator instead. So if I multiply the entire integram by c1, I must divide it by c1. So let's divide it by c1 like that. And let's let c2 over c1 equal c3. So now another constant, c3. And yeah, let's just do that. So integral equals 2 over c1 times the integral of 1 plus t squared plus c3, sorry, not c cubed, c3 dt. And I'll write c3 in red, why not? Now, should we take a substitution? Let's say tangent of u, yes, u is equal to t. And let's put the square root of c3 as a constant multiple in front of the tangent of u. So that this would imply that c3 multiplied by tangent squared of u is equal to t squared, right? Now, if we must implicitly differentiate both sides, so dt is equal to du multiplied by secant squared of u multiplied by the square root of c3. Now, if I rewrite everything in terms of u, I get I equals to 2 over c1 integral of 1 over t squared plus c3. And instead of dt, I can write the square root of c3 secant squared of u du. Now, you see the c3 here. I can actually rewrite it as the square root of c3 squared. I'm not really doing anything. I'm just like writing it in a nicer form, really. Nothing special, nothing special. Wait a second. Wait a minute. Instead of t squared, sorry, I should write c3 tangent of. Okay, never mind. I don't need to do anything. I just need to replace the t with c3 tan squared of u, and then the plus c3 I can keep it as plus c3. Yeah, just like that. Simple. Now, because the root c3 is a constant multiple, I can just factor it and bring it out of the integram. So 2 root c3 over c1 integral of 1 over this bit c3 times, I'll underline it, c3 times tan squared of u plus c3. We can factor out c3, and you end up with c3 multiplied by tan squared u plus 1 secant squared u du. And this c3 we can bring it on the outside. So I is equal to 2 root c3 all over c1 c3 integral 1 over trig identity time. This tan squared of u plus 1 is equal to secant squared of u, right? I'll just write on the side. Tan squared of anything, let's say beta, plus 1 equals secant squared of that very beta. Beta male, I know, very funny. And remember, we still have secant squared u du. If you cancel out the secants, you just end up with du. And if you integrate du, this is basic baby integral. You end up with just u, of course with the constant in front of the u. So c1, c3, u. And now all we need to do is bring this u back into t and bring the t back into x, and then replace the constants c1 and c3 with in terms of a and b, basically. So now what do? Let's first replace the constants. Actually, let's first replace the variable, then we can focus on the constants. So if we have like this, what is u equal to? Well, if we scroll up for a second, root of c3 tan of u equals to t. So if I write that here, root of c3 tan of u equals to t. Let's divide both sides by c3, so that tan of u equals t over root c3. Did I say divide by c3 or did I say divide by root c3? Well, nonetheless, I meant root c3. And then let's apply arctan to both sides. U is arctan of t over root c3. So if I replace this u here with all this, you get arctan of t over root c3. And that t can be replaced in terms of x. Remember that here, t is equal to, let me just write it nicely. T is equal to tan of x over 2. So I'll just use green. T is equal to tan of x over 2. So what can we do? We can rewrite this, the answer to the integral, in terms of x instead of in terms of t. So we have arctan of t, which is tangent of x over 2, and we have all over root c3, which I can write as like this: 1 over root c3 multiplied by tangent of x over 2 in the bracket. I know we have a tangent within an arctangent, and I don't think we can really simplify that unless you use the log form, but then that just gets confusing. This is confusing on its own. And now, just for fun, let's replace the c's with a's and b's. So just as a reminder, we said that from earlier, let me just scroll up, a minus b equals c1 and a plus b equals c2. Just the a and the b from the original integral. A minus b equals c1 and a plus b equals c2. We also said that let c2 over c1 equal c3. So c2 over c1 equals c3. There. Now, I'm going to rewrite the c3s in terms of c2 and c1. So this c3 becomes c2 over c1. The same thing happens to this c3. So c1, c2 over c1. And you notice the c1s cancel there, like that. Very nice. Then we have the arctangent of 1 over root c3, which is root of c2 over c1, tangent of x over 2 still. We're nearly done. We just need to, because I like consistency, I need to keep the answer and the question in terms of the same things that we started off with. It's nice to do that. And if c1 is equal to a minus b and c2 equals to a plus b, we end up with 2 root of a plus b over a minus b over c2, which is a plus b, times the arctangent of 1 over the square root of a plus b over a minus b, times the tangent of x over 2. And that's the answer. We got it, right? That's it. And just to end off the video, I'm going to write everything in one line. So the integral of 1 over a plus b cosine x dx is equal to 2 root a plus b over a minus b, all of this divided by a plus b, and multiplied by arctangent of 1 over root a plus b over a minus b, tangent of x over 2. Plus c. I forgot plus c. Let's use plus c 4, because I've already used c1, c2, and c3. In this situation, c4 is just the constant of integration. So that's the answer. Now the mathematician has done his work. The mathematician should give his work to the physicist who will complete this. Thank you for watching this video. Once again, like, subscribe, share, and whatnot. And enjoy your day.